Well, good afternoon, grade 12s. All right, so moving on with the unit this week. Here's how it works, okay? So what we've established so far is that back in the late 1600s, early 1700s, there was so 300 years ago, there was two competing theories on what light was, okay? And one of them was a particle model that Newton came up with. The other one was a wave model that Christian Huygens came up with. And, basically for the next 200 years, they taught Newton's model in school, mostly because they had no evidence either way, but Newton was considered more famous, okay, and more brilliant, okay, than Christian Huygens was. And so they went with that theory. Now, it's not the way science is supposed to work. I mean, we should be able to just say, well, we're not sure about this, and these are the theories that are on the table, but that's the way it worked. And then 200 years later, in the mid-1800s, some evidence came to light, okay, that Huygens was right, actually. Okay, now I mentioned that in the last video. So now what we're going to do is we're going to move away from talking about the particle theory of light altogether, because Newton's theory was not that great, actually. Okay, so we'll come back a little bit later when we do quantum physics. We'll see that maybe he was on to something there, but basically the evidence that was discovered in the 1800s was completely overwhelming that light behaved like a wave. Okay, and he was totally right about how refraction works. So Huygens thought that light would slow down when it entered glass. Okay, and it really does, and they discovered that in the late 1800s when they were able to measure the speed of light. And they're also able to show that light waves produce interference, and then case closed, light's a wave because only waves interfere, okay, with each other. And so we'll talk about interference. That'll be our next topic, but for now we're just going to talk about refraction, okay? And I actually have a worksheet for you. It doesn't take very long. It's really, I give this worksheet out in grade 10, and you're supposed to do refraction in grade 10 when you do optics. Okay, now some of you may or may not have done Snell's law, so unfortunately in grade 10 you don't have the best knowledge of trigonometry yet, but you guys are experts, and so you'll get this, okay? All right, so here's the deal. First of all, it's good to know what refraction is. Refraction is what happens when light, or waves in general, go from one medium into another medium, and what happens is they change speeds, okay? And when they change speed, okay, they change direction. Okay, now that's when they come in at sort of an incident angle that is not 0 degrees. In other words, if they're coming in like sort of on an angle and they hit the medium, they'll change direction. We won't notice a change in direction at all if they come sort of straight along the normal line and they just sort of go straight through, but they do still slow down. They just don't change direction just because of the direction of their travel there. Okay, so they slow down no matter what, but they don't, in the case of, let's say, light going from air into glass, it slows down no matter what direction it's coming from, but it doesn't necessarily change direction. It will only change direction. It will change direction at any angle except for 90 degrees to the interface, right? Like, so in other words, if it's right along the normal line. All right, so I was actually, before I start this video, I'm going to show you a picture of refraction. Okay, so just so you get some sense of what we're talking about here. Here, let me find a good one. All right, this one's all right. I like this one. Okay, so I'm just going to put that in your note, just so you got some sense of what it is that we're really talking about here. All right, so here's a picture of light refracting through a glass block. And there's a beam of light. That's an experiment that you can show the kids in grade 10, typically. They're in grade 12, so this is just a quick review of something that you learn in grade 10. All right, so let's get right to it. So if you're in my grade 10 class, this would ring a bell. But listen, why do waves change direction like this when they go from one medium into another? It's because, like I said, they change speeds, okay? So if you're driving your car and, like let's say, here, this is the best analogy I can give you. Let's say this is the top view of your car. Here's your 4 wheels of the car. So you're sort of seeing an X-ray of the car, okay? Let's say the car is traveling this way. Well, if this wheel here, if that wheel touches the gravel and slows down, what will happen is the car will turn towards the slow area, okay? And really that's what waves do, okay? They turn towards the, I'm going to erase this, is not a very good example, it's going to confuse people, so, you know, it turns towards the slow medium. If you like it, the wave that enters the part of the slow medium first, these waves here, they trail behind because they're moving slower, okay? So here you can see these waves that have entered the new medium. And they also get closer together, which makes sense when you slow down, right? So if you're ahead of me and you slow down, and then I will gain on you, and then if I have to slow down too, then we'll be a new distance apart, okay? And that new distance will be the wavelength, the new wavelength in the new medium. All right, so here's the deal. I'm just going to write down just a couple of notes. Refraction, which is the change in direction. When entering a new medium, okay, happens, I should write a new sentence here. This happens because of changes in speed. Okay. All right. So anyway, you can see this little diagram here. We call this angle up here, I'll just circle it, that theta 1. Theta 1, whoops, I usually call it theta I. It's the angle of incidence. So, pardon my spelling there. This is called the incident ray. Okay, on this picture. You're not going to have to, in grade 10 I make them label it, but you won't have to label it here. This ray over here is the refracted ray. With light we only see the rays. Okay, we don't actually see the waves themselves. So in this picture here, if you want to, the waves are actually like this, okay? But you don't see them. Okay, and then they change direction here, okay, and they're closer together in that medium there, and then they sort of change direction again when they go back into the air. Okay, and they spread apart. And so you don't see the waves, but we do see the rays of light. So we actually see these rays here, okay? We don't see the waves that go with them, but they're there, okay? They're there, and that was Huygens' brilliant sort of insight, okay? All right, so this happens with changes in speed, okay? And, you know, this line here that we call the normal, that normal line, we measure our angles from the normal line. That's kind of important. All right. So anyway, Snell was another scientist that was arrived on the scene. I don't know if it was. I'm not sure of his age. If he was certainly it was after. I think it was after Christian Huygens was alive. But anyway, you can study waves of this. It's not just unique to light, right? Like this phenomenon of refraction occurs with water waves and other types of waves too. So anytime a wave slows down, like water waves slow down when they go from deep to shallow water, okay? And if they come in at an angle, they'll change direction, okay? And this occurs all the time in the ocean, okay? So like when waves roll into shore, okay, they will refract, okay, and they'll change direction. So Snell's law, okay, Snell's law describes the nature, like the relationship between the angle of incidence, the angle of refraction, and the ratio of speeds. Okay. Now I could go through the derivation for you. Sometimes I do that, but you know what? We don't have time for that. So let's just do it like this. What he found was that the sine, mathematically, you're able to prove this. The ratio of the sines of the two angles, angle of incidence, this one here is theta r, is equal to the angle of refraction, okay? that will equal V1 over V2. Okay, so here in the incident media, these waves are moving at a speed of V1, and here they're moving at a speed of V2. Okay, so they slow down, and it turns out that the ratio of the angles is equal to the ratio of their speeds. Now, the universal wave equation tells us that speed is equal to frequency times wavelength. So you can write it like this. Now, the frequency of the waves does not change. That's determined by the source, okay, of the waves. And the frequency will not change when you go from one medium into another. It's a little non-intuitive, but that's how it works. The wavelength, though, if you look at it, the distance between the waves here is definitely changing. Okay, they're further apart in the faster medium and closer together in the slower medium. Okay, so the frequency cancels out there, and we get that. All right, and now there's another variation on this law that's especially for light, where it's equal to n2 over n1. And now I'm going to explain what n is in a second. This is, I'm going to circle this. This is for light only, okay? Because there's, I'll have to explain to you what n is, okay? And then you'll understand what I'm trying to say here with light. But yeah, n is what's called the index of refraction, okay, of the media. And I'll explain that in a moment. Okay, so for light only, it works like this. Now this here, this for these two, all waves, water waves, waves in a string, whatever, well, in a two-dimensional media at least, okay? One-dimensional waves won't change direction because they only have one dimension to travel along, okay? But they still slow down and entering a new medium. Okay, but anyway, all other waves, water waves, etc., okay, sound waves, and so on, you can use the other two versions of this equation here. The ratio of speeds or the ratio of wavelengths equals the ratio of sines of the angles. But for light, we have a special version of it. And I'm just going to define for you now what n is. N equals the index of refraction. So here's the deal with light. Okay, we know that the fastest light can travel is in a vacuum. Okay. So C equals 3.0 times 10 to the 8 meters per second. That's equal to the speed of light in a vacuum. Okay, that means in like outer space. Okay, so light travels fastest. This is the fastest possible speed. Okay, when light enters glass, it slows down. Okay, and that's what Huygens was saying, right? It slows down. In fact, when it enters any other medium, it slows down. So what's happening really, if you really want to know what's happening, which Huygens didn't quite understand at his time, but what's happening there is that, remember that light is a disturbance in an electric field. So you see atoms have electric fields around them. And so in optical media, the interaction of the light wave with the electric fields of the atom will tend to produce a kind of drag on the electromagnetic disturbance. Okay, so what happens is that slows down the propagation of the light wave, the presence of the electric fields around those atoms. Okay, now you don't need to know the explanation. That's not really that important as long as you can sort of do the math here. Okay, it's kind of cool how it works. So I want you to care about the explanation, but like we don't have time to get into all the details of it. Okay, so this is just a review of a grade 10 concept, so I just want to spend a few minutes doing it here. Okay, so anyway, the index of refraction, the definition of it, it's defined as the speed of light in a vacuum divided by the speed in a medium. So Nm is called the index of refraction for a medium. Okay. And then Vm is the speed of light in the medium. Okay, and C, of course, is 3.0 times 10 to the 8. It's the speed of light in a vacuum. Okay, now the deal why do we do this? Why do we define this concept? So this is, the definition of the index of refraction. Well, we're just saying, look, let's say Usain Bolt is the fastest runner in the world. He's got the world record, right? Say for the 100-meter dash. So that's the fastest man alive. So what if we indexed all of our running speeds relative to him? Okay. So let's say, for example, if I am 50% slower than him, okay, then the index of me compared to me would be 1.5. Okay, so his speed divided by my speed, I get 1.5. In other words, he's 1.5 times faster than me, right? So that's what we're saying. Okay, so let me give you an example of this. Okay, typically glass. Okay, let's do water first. This is for H2O. Now, the index of refraction is a ratio of two speeds, so it has no units. Okay, and what it means is that the speed of light in a vacuum is 1.33 times faster than in water in its liquid state. Okay, so if that's logical to you, that's the definition of index of refraction. Now, of course, we could actually find the speed in the water. Okay, we could just go like this. Therefore, the velocity would be c over 1.33, right? Just solving, okay, for the velocity in the medium. Okay, and then you could just take out a calculator and you just go 3 times 10 to the 8. Okay, 3 exponent 8 divided by 1.33 is 2.26 times 10 to the 8 meters per second. That's still very fast, okay? Just not as fast as it is in a vacuum, right? So anyway, that's the index of refraction. Now, you understand, hopefully, Snell's law here, okay? The ratio of speeds will go by, like, that's not a typo that I didn't make a mistake by putting n2 over n1. It's because n is on the bottom of this fraction that it works out that way, okay? So remember that refraction happens because of differences in speed. And so that's where that comes into the formula here, okay? All right, so that's basically the lesson. I wanted to show you, I did post a worksheet. It doesn't take, there's lots of questions here. There's like 13 questions. It doesn't take that long. They're just quick calculations. Okay. Anyway, at the top here, they show you some indices of refraction. Okay, so an air or a vacuum, it's 1.0. It makes sense. So air has approximately the same speed of light as in a vacuum. Water's 1.33, like I told you. Crown glass, 1.523. See, I don't know what CR39, probably plexiglass or something. Okay. Barium glass 1.6, flint glass 1.7, so there's different kinds of glass. Okay, polycarbonate 1.586, diamond 2.45. It's got a very high, light travels very slowly in diamond. Okay, there's something called zircon, which is basically like a gemstone, and that travels at like 1.9. Okay, the index of refraction is 1.9. So anyway, there you go. Now, if you are doing these questions, all you have to do is use a formula. So it says light is traveling from air, so that means you use the table. N1 will equal 1.0 into crown glass, so using the table, so N2 would be 1.523. Okay, strikes the surface at an angle of 30 degrees, so that would be theta I. The angle of incidence is 30 degrees. And what they're asking you for is, what is theta r? Okay, so what you do is you use this equation, sine theta I over sine theta r equals n2 over n1. Or if you like, you could just cross multiply. Anyway, I'm just going to do the algebra really quickly because I got to go to the bathroom, so I'm trying to end this video. But anyway, sine theta r will equal, if you just quickly do the math, it'll be n1 sine theta I divided by n2. Okay, so you can just go ahead and do that. Those are really easy worksheet for a grade 12 student to do, but we need this to move forward in the wave theory on light. Okay, so the rest of this unit we'll be talking about the wave theory. We're going to spend a lot of time talking about interference, but for today, just a little review of grade 10. And that's it for now, okay? And then tomorrow I'm actually going to post another lesson to round out my 3 hours this week, okay? And we'll move on from there. All right, guys, that's it. Enjoy your day.